Okay, so now let's begin with the ionic polymerization part. So when we first learned about the addition polymerization, we have briefly learned that there are three different kinds: free radical, cationic, and anionic polymerization. So previously we have learned about free radical polymerization, their its phasic feature, kinetics, and molecular weight distribution, etc. Okay, so now it's time to begin with ionic polymerization. So let's first compare free radical and ionic polymerization. Okay. So the major difference is that number one, free radicals are free, but anionic and cationic groups have counter ions associated with it. Okay? So if you perform a polymer synthesis inside of the liquid using you can just use liquid phase monomer, or you can use solvent. Anyhow, electronic charge should be balanced, right? Overall electrical charges should be neutral. So if there are some amount of cations or anions, there should be counter ions which can balance the counter charges, right? Which means that if there are polymer chains with the end group of a certain chemical charges, positive or negative, there should be some amount of counter ions which have the opposite charge. Okay, so that makes the ionic polymerization much more complicated because of these interactions between counter ions, and especially this association between counter ions depends on many different factors: stability of end group, types of counter ion, what kind of the kinds, and polarity of reaction medium, temperature, etc. So which means that all these variables affect the behavior of this ionic polymerization that tend to make things much more complicated. Furthermore, these counter ions, the counter ion pairs affect many things: reaction rate, termination rate, stereospecificity, and copolymer reactivity ratio, which will be covered when you learn about copolymerization. When you learned about free radical polymerization, we didn't really care about solvent, right? Especially solvent polarity. But in ionic polymerization, even solvent polarity, if you use polar solvent or non-polar solvent, affect the many different features of the polymerization process. Okay. So, if you recall free radical polymerization, there was generalized mechanism, right? Initiation, propagation, and termination. That was all, right? Also, in terms of kinetics, it was relatively easy, right? We only assumed the steady state, not really assumed. It was experimentally valid assumption. Anyhow, we could use steady state approximation, and we could get the expressions for example, propagation rate, kinetic chain length, etc. But for ionic polymerization, detailed mechanism depend on many different things: what kind of initiator we are using, what kind of monomers are using, what kind of solvent we are using. So, which means that it's really complicated, right? No general mechanism. Second difference between free radical and ionic polymerization is that termination mechanism vary among these species: free radical, cationic, and anionic. For free radical and cationic polymerization, the termination mechanisms are similar. They have combination and disproportionation. But the result is a little bit different actually. when you learned about free radical polymerization, for combination, we basically combine the two living free radical chains, right? They form dead chains, which with a longer chain length. Okay, but for cation polymerization, here is the polymer chains with the positive ion. With the this is a counter anion. Okay. These tend to just die, tend to lose this positive ion. It could just form just dead chain by reacting with this a portion of this counter ion, but the molecular length is basically same, right? Similarly, you can just form this double bond. Overall, the chemical structures are different, right? At the end, right? But the molecular chain length is quite same, right? On the other hand, anionic polymerization have no termination step. When you start anionic polymerization, unless you like purposely put in some like additional materials to stop the reaction, that anionic polymerization does not stop. So that's why we call it living polymerization. So we'll learn about this in more details later when you learn about the anionic polymerization. And third difference, let's move on to the next page. Third difference is that concentration of the growing polymer chain is much higher in ionic polymerization than free radical reactions. So if you compare the concentration values in free radical polymerization, the free radical concentration inside of the reaction media is in the order of like 10 to minus 8 to 9 mole. It's relatively small concentration, but for cation or anion, it's much higher concentration compared to this value, right? So if you have much higher concentration of these species, which means that the propagation rate is much faster in ionic polymerization compared to free radical polymerization. So we learned that in previously, when you learn about free radical polymerization, we learned that free radicals are extremely reactive. So within a few seconds, we can achieve like 1,000 monomers attached to the growing chain, right? But in ionic polymerization, even the rate is much faster than free radical polymerization. So RP is really high even at low temperature. Okay. Fourth difference is preparation method are different much more for free radical. So we haven't learned about this processing condition for polymerization, but anyhow we learn about this at the end of this semester. For free radical, gas phase, solid phase, even liquid phase can be used to make the polymers, but for ionic polymerization only in liquid phase generally used. Okay, this is not that important, but the other three features are quite important and also quite interesting, right? Although all these three polymerization methods are addition polymerization, depending on what species we are using, their features are quite different. Okay, so now since we have seen the main differences between free radical and ionic polymerization, so let's see more details about ionic polymerization first. So from here, ionic polymerization. So there are two different kinds, cationic and anionic. Okay. So let's first see the main features, their similar features and their differences. First one, similarities. So ionic polymerizations are much more selective than free radical polymerization. which means that we cannot really use any chemical structures to make polymers. Sorry. So let's go back. So if you compare the cationic and anionic polymerization, their similarity compared to free radical polymerization is they are more selective, which means that they depend on the structural monomer. I mean, when you make polymers based on free radical polymerization, generally any monomer structures are possible. But for ionic polymerization, the selection of the monomer structures are kind of limited. Let's see an example. For example, let's say that we doing the cationic polymerization. There is a cation, okay, and cation react with the monomer. It's also the vinyl monomer, right? It forms active center, as you have learned from free radical polymerization. It's basically same, right? There's only difference is there's a positive ion here. Okay, previously there was a radical here. Okay, in this case, the selection of this R group is limited. Okay. The reason why is that since there is a positive ion here, if this R group is, for example, electron withdrawing, so you remember the electron donating and electron withdrawing group from organic chemistry class, right? So if R group is electron withdrawing, then this carbon with positive ion, this carbon does not have electrons, right? It's positive ion. And if this R group is electron withdrawing, basically withdraw electrons from neighboring carbon, then what would happen? This carbon will be much more unstable, right? So that tends not to happen, right? To stabilize this structure, this ionic structure, this R group should be electron donating to stabilize these cations. Okay. Similarly, if you form, for example, like anion, reactive active center of anion, this minus ion here, this R group should be electron withdrawing. Okay, there is enough electron here. If this R group is electron donating, then I mean already this carbon has much more electrons compared to other neighboring atoms, right? They don't. I mean, this carbon does not need additional electrons, right? So this R group should be electron withdrawing in the case of an ionic active center. Okay? That's why we call it more selective. And we already have seen that counter ions are present, right? For polymer chains with carbon positive ions, there should be some negative ions attached to it closely. For anions, there should be positive ions attached to it. Another features, reactions are really fast, but extremely sensitive to small amounts of impurities. Okay? So if there are, so basically the purity of the monomers and the reaction medium is really important. If there is some amount of impurities, that might stop the reaction. And we already have seen that the formation of relatively stable ions is important. That's why the structure of R groups, side groups are very important, either electron donating or electron withdrawing groups. And since it is really like the propagation rate is extremely fast, we generally perform the ionic polymerization reaction at low temperature. but there is a difference between cationic and anionic polymerization. We have learned that the cationic polymerization have basically similar termination mechanism to that of free radical polymerization, right? Combination and disproportionation. But for anionic polymerization, there is no termination. That's why we call leaving polymerization. So anyhow, we haven't really learned about the details. So let's move on to the more details on each of these ionic polymerization. So the first is cationic polymerization. Cationic first. For cationic polymerization, there are also three distinct steps, as we have learned from free radical polymerization: initiation, propagation, and termination. Okay, let's see one by one. So for initiation, similar to that we have learned from free radical polymerization, in this step we need to make cation, right? And for free radical polymerization, we used some initiator, right, which can generate free radical by heat or by light, right? Similarly, cationic polymerization requires some initiators, and there are mainly two representative initiator. The first one is protonic acid. So basically, acid which tends to provide hydrogen H plus ion, right? So which basically is something like this, very strong acid. Okay, if this strong acid react with monomer, okay, then this strong acid basically provide this hydrogen H plus ion, okay, basically forming this cation. Okay, and this one is just counter anion. Okay. Another initiator is Lewis acid. Okay, you remember what Lewis acid is, right? From general chemistry class, right? When Lewis acid is used as initiator in cationic polymerization, usually co-catalysts are needed. Co-catalyst is basically some compound which just helps the role of this Lewis acid. So for co-catalyst, compounds such as water, protonic acid, and alkyl halide are used. So let's see an example. So Lewis acid is BF3, and let's say that we use water as co-catalyst. So if these two compounds react with each other, they form this structure compound, H plus BF3 OH minus. Okay. And if this compound react with monomer, then this hydrogen ion can be attached to something like as similar to this the formation of the carbon ion. Okay, sorry, carbonium ion. Okay. Another example is AlC3, also an example of Lewis acid with co-catalyst and forming this structure. And if this compound reacts with monomer, this positive ion is attached to the monomer. Okay. So anyhow, overall, we are basically using acid, protonic or Lewis acid, as initiator for polymerization. Cationic polymerization. So as I mentioned, that this compound can react with monomer and forming this kind of structure. I already mentioned it, right? And next step is propagation. Okay, the formation of the long chain polymers. Okay, so once we have this kind of active center with cation, okay, and they tend to react with monomer one by one in a head to tail manner. Okay, so the overall propagation mechanism is the same as the free radical polymerization, just addition of monomers one by one, forming long polymer chains. And the problem is, as I mentioned before, ionic polymerization is much more complicated. So the the propagation rate constant or mechanisms depend on many different factors, such as monomer structure, count ion type, solvent, polarity, temperature, etc. No general propagation mechanism. So third is termination. Okay. So we already have seen that for cationic polymerization, combination and disproportionation can occur. So unimolecular rearrangement of ion pair from these polymer chains with carbon cation, they can just rearrange themselves, basically giving this positive ion into basically this counter ion attacks this hydrogen ion, forming this structure and initiator structures. Or chain transfer can also occur. Okay, basically cation chains react with monomer and this monomer becomes this cation, and this reaction just ends here. But the problem is, I mean, as written here, exact mechanisms for terminations of cationic polymerization are not properly understood. Because, I mean, as shown here, there are numerous side reactions, mostly chain transfer. This kind of chain transfer can occur between polymer chains and monomer, solvent, or another polymer, etc. So in cationic polymerization, only short chain are obtained. It's really difficult to achieve high molecular weight long chain polymers. So if you want to achieve high molecular weight polymers using cationic polymerization, you can use low temperature, because high temperature tends to make these side reactions occur more frequently, but it's not really 100% efficient. Okay? So overall, the cationic polymerization have same three distinct steps: initiation, propagation, and termination. But the problem is, detailed mechanisms are not known. Okay, so we can just briefly understand the main features. That's all. Okay, so let's move on. I'm going to just skip this part. Let's see a little bit about the kinetics. Okay, although we don't really have the exact mechanism, we can briefly understand the kinetics of the cationic polymerization. So for initiation, okay, as you remember, the protonic acid basically form H plus and anion, and this is reversible reaction. So with the equilibrium constant K, and this initiator reacts with monomer, forming active center. And the second reaction among these two, second reaction is rate determining step. This is slower. So the initiation rate can be written like this. Okay, if you can just rearrange these two, rate equilibrium constant and the initiation rate constant. Okay, and propagation reaction of this with monomers forming a longer chain. Okay, so we can write the propagation rate similar to free radical polymerization. Okay, termination. Let's say that we just consider the spontaneous decomposition, the unimolecular rearrangement, and that's shown here. And we can just write the termination, which tends to be just unimolecular, right? If we consider chain transfer to monomer, then the termination rate can be written in this way, right? Monomer, cation concentration and monomer concentration, right? It should be bimolecular. Okay. Then overall reaction rate of the cationic polymerization should be propagation rate, right? But there is cation concentration, right? Which is not really useful, right? So similar to that we used in dealing with free radical polymerization, we can use steady state approximation to replace this cation concentration part, right? So let's use the steady state approximation. We can simply take this initiation rate and the termination rate same. Then we can get this expression as shown here. And if you put this into here, okay, then the propagation rate can be written like this. Okay. Okay. If you compare the propagation rate of the free radical polymerization, it had this form, right? Remember? Okay. If you consider termination by chain transfer, then the over the expression just changes from square to just 1. That's all. Okay. And kinetic chain length. So similar to we can just use the same definition that we used in dealing with kinetic chain length in free radical polymerization. You remember, right? Kinetic chain length was defined as the propagation rate divided by the initiation rate or termination rate, right? So we can just use the initiation rate here and termination rate here. Okay, you just if you divide it, you can easily get kinetic chain length as shown here. Okay, and kinetic chain length, if you only consider unimolecular rearrangement for termination, then they should be same as number average degree of polymerization. If you consider termination for chain transfer to monomer, then the number average degree of polymerization becomes Kp over Ktr independent of the monomer concentration. Okay. Okay. Temperature effect. You can do the similar approaches that we used in free radical polymerization. You can just simply express the rate constant for initiation, propagation, and termination using Arrhenius equation, right? Okay, so if you use the Arrhenius equation, you can just have this kind of activation energy dependence of overall reaction rate or number average degree of polymerization, RT and Xn bar. Okay, and generally, the for cationic polymerization, activation energy for termination is much larger than EI and EP, the activation energy of propagation and initiation. Okay, so which means that this value is much larger. This value is much larger, right? Which means that as you increase the temperature, reaction rate decreases, and also the number average degree of polymerization decreases. Okay. Or if you decrease the temperature, you can increase the reaction rate and also average chain length. Okay, so that's different from free radical polymerization. Okay, so this is pretty much it for cationic polymerization. So overall feature for cationic polymerization is quite similar to free radical polymerization. 3 distinct steps. And only difference is there is a counter ion and the initiators are different, but the major procedures and the things that we cover is pretty much same, right? And detailed mechanisms are not really understood for cationic polymerization, so that's why we just kind of briefly skipped over the cationic polymerization part. Okay. Okay, so now it's time to move on to the anionic polymerization part. So we have seen that cationic polymerization have pretty much similar features to those of the free radical polymerization, right? Then how anionic polymerization is different from cationic polymerization. At first, as we already have learned in previous lecture, that in anionic polymerization, monomers should have the side group of the monomer should have strong electron-negative group, electron withdrawing group, right? To basically with this electron withdrawing group, they can stabilize the minus ion inside of these anions. Okay, that's the main feature. Okay. Similar to free radical and also the cationic polymerization, there are also three distinct steps: initiation, propagation, and termination in anionic polymerization. Okay. Let's consider one by one. Initiation. Okay. There are many three different initiation mechanisms in anionic polymerization. The first one involves base. As you remember, for cationic polymerization, as an initiator, we used acid, right? Protonic acid or Lewis acid, right? In a similar manner, for anionic polymerization, we use base as an initiator. For base, either alkali metal amides or organon lithium are used. So these alkali metal amides, such as like KNH2, basically K plus and NH2 minus, right? So this NH2 minus strong base, okay, can react with monomer, forming anions. Okay, and this reaction occurs in liquid ammonia as solvent. Okay, and this anion is kind of free ion, similar to free radical, because I mean, if you only consider this reaction, there is no counter ion, right? The second reaction is between monomer and organolithium, such as N-butyl lithium in benzene solvent. Okay. So remember, I mean, if you remember organic chemistry, the N-butyl lithiums are commonly used, right? N-butyl lithium, strong base. Okay, so this is N-butyl lithium. Okay, lithium positive ion and butyl lithium negative ion. It can react with monomer, okay, forming anion and lithium plus counter ion. So by the reaction itself, they tend to make these ion pairs. Okay. Initiation of anionic polymerization can also occur by electron transfer. For example, alkali metal with aromatic compound in ether solvent, for example sodium, can react with naphthalene, okay, forming this kind of sodium naphthalide. It's radical anion. Okay, there's a positive ion here. So basically, this sodium transfers one electron into this naphthalene. Okay, so forming this kind of sodium naphthalide structure. And then this sodium naphthalide radical anion, this one, react with the monomer, okay, forming this kind of radical anion sodium ion pair and forming benzene. Okay, and since this is not stable structure, right, there is a 3 electrons, 3 and 1, this is kind of a radical anion, right? So they tend to react with each other, okay, so basically forming dimers, forming dianion, okay, 2 anions on each end. Okay, so basically this initiator can react with monomer on this side and also on this side. Okay, this is just dianion. Okay, so there are the three different initiator structures, and this dianion is quite interesting, right? From single initiator, we can basically do the reaction on both sides, right? So this is the initiation part. Next is propagation. So this, depending on these three initiator, free ion, ion pair, or dianion, they can just react with monomer, okay, forming longer chain. Okay, forming longer chain. But as I just mentioned, this anion case, chains can be added on both ends, right? That's the difference between these two cases. Okay. And the most important thing about this anionic polymerization is termination step. Since each of these polymer chains have negative charges, okay, without any impurities or some other species, these negative centers, because of electronic repulsion between them, they cannot terminate with each other. Okay, that's why we call anionic polymerization as living polymerization. It does not die. Okay, to make it stop, to make anionic polymerization stop, we need to deliberately add impurity, such as oxygen or carbon dioxide or water. Then these impurities react with these anions and it can stop, it can kill the polymerization reaction. Okay. Let's see the next pages for the examples of this termination by impurities. As you see here, these anionic chains can stop the polymerization, the anionic polymerization, either by reacting with proton, carbon dioxide, or want to dibromomethane, or this is limiting amount, excess amount and limiting amount of dibromomethane. Okay, so anyhow, I mean, we need to purposely add some chemical species to stop the anionic polymerization. Without them, it does not stop. It's living polymerization. Okay, let's go back. And another important feature about anionic polymerization is that initiation rate Ri is much faster than propagation rate, which means that at the beginning of the reaction for anionic polymerization, the initiator, basically anions are formed immediately. All the anions are formed immediately after the start of the reaction. Then at the end of each of these anions, polymer chains start to grow. So basically all chains start at almost the same time grow at a really fast rate. Okay, so if there is no chain transfer or no termination without any impurities inside of the reaction vessel, then each of these polymer chains formed by anionic polymerization would be basically same size, same molecular weight, and same molecular length. Okay, so this anionic polymerization, this living polymerization, can generate almost monodispersed polymers. If you recall free radical or step growth polymerization, there were molecular weight distribution, right? both of those polymerization methods have most probable distribution, right? Something like this, right? Depending on the molecular weight. There was some distribution. Some of them are longer chain or high molecular weight. Some of them are low molecular weight or shorter chains. But anion polymerization can possibly generate almost monodisperse polymers with PDI is almost 1. Okay? In theory, I mean, we will not go into the details about this theory, but in theory, PDI in anion polymerization is equal to 1 plus 1 over number average degree of polymerization. So if you have high molecular weight, this is almost basically 1. Okay, you can just ignore this part, right? It's a very interesting feature, right? Anion polymerization can possibly generate monodisperse polymer. You remember that if you want to make monodisperse polymer, we need to do the polymerization reaction in space, right, without any gravity, right? But anion polymerization can solve those limitations. Next feature is kinetics. And similar to cationic polymerization, kinetics of anion polymerization is also not much studied. Okay? Only reaction studied is amide ion initiated polymerization in liquid ammonia. When you just the first case of the initiator, right? There were 3 different kinds, right? Amide in liquid ammonia and the organolithium case, and also the electron transfer case. Okay. So we'll not go into the details about this, the derivation of the kinetics equations, but just briefly the result. The propagation rate has, for example, like this form, and the number average degree of polymerization has this form. Okay. So I mean, that is the reason why I just kind of skip this part. It's not that important, right? This kinetics part is not important because it's not well understood. Temperature effect. Also, we can just check this temperature effect if you have information about the rate constant of each step, right? By comparing the activation energy of the initiation, propagation, and there's no termination, but anyhow we can just check this temperature effect, and the overall result is basically same as free radical polymerization. As you increase the temperature, you tend to increase the propagation rate, but tend to decrease the number average degree of polymerization. Another feature is this is actually much more important than this part. The number average degree of polymerization, basically the average chain length that you can obtain using anionic polymerization. The calculation is very simple. To calculate this, we can use this information, right? The all chains start at almost the same time, basically forming the almost monodisperse polymers. Based on that information, if you consider monoanionic propagation, the first 2 cases in the initiation part, the number average degree of polymerization should be equal to the concentration of monomer divided by the initiator concentration, right? Because all initiators start at almost the same time. Okay. If it is anion propagation, we can just simply multiply by 2, because basically we are making double chains, right, on both ends of the initiator. Okay. So although I skipped this kinetics part, if you are interested, you can do the derivation, is in the next slide. I'm going to just briefly explain it. Okay? If you're interested in the deriving this result, the RP and degree of polymerization, why we get these expressions, I already did it by my hand, as shown here, kinetics part. Okay, so this is the initiation, propagation, and termination part. Okay, so we are only considering the strong base, the amide, potassium amide, in liquid ammonia. So the first reaction is the reversible ones forming K plus and NH2 minus. And this NH2 minus react with monomer, okay, forming anion active center. And in this case, the second reaction is rate determining step. Okay, so it has the initiation, the rate constant Ki, and here I can also denote the rate constant K, sorry, equilibrium constant. For propagation, this anion react with monomer, forming longer chain, right, with rate constant of Kp. If you only consider termination of chain transfer to ammonia, okay, as shown here, the anion chain react with ammonia, forming the dead chain and NH2 minus, which can be used in the initiation step, right, with the rate constant of KTRS. Okay, still, as you see, overall kinetics part is pretty much same as the one that we used in cationic polymerization part, right? Okay, so the overall the propagation rate or polymerization rate of this anionic polymerization can be written by these expressions, and since we do not really want this expression, ion concentration, we can simply use steady state approximation by just saying that the initiation rate and the termination rates are same. Okay, then you can replace this concentration using these equations and you can get these expressions as shown in previous slide, right here. Okay, this one, it's pretty much same procedure that we used in dealing with cationic polymerization. Okay, finally, we already mentioned that in anionic polymerization we can achieve almost monodisperse molecular weight distribution. Okay, and in theory, I mean, we will not do the derivation using detailed theory, but anyhow, if you check the textbook, there is a detailed derivation of this result. If you want to derive the molecular weight distribution in this living or anionic polymerization, the number average degree of polymerization have this equation form, which is called Poisson distribution. And if you plot this Poisson distribution, so this Poisson distribution as a function of the number of chains, then let's say that it has this form. And if you compare this with normal free radical polymerization, which had most probable distribution, remember, like P n minus 1 times 1 minus P, something like this, right? So this form have much broader molecular weight distribution compared to anionic polymerization. That's why we call this we consider the anionic polymerization as kind of like we can just generate almost monodisperse polymers, which have much narrow molecular weight distribution compared to free radical or step growth polymerization method. So as I mentioned, the PDI is this form, 1 plus 1 over number average degree of polymerization. Okay, so almost 1. Okay, so this is it for anionic polymerization, right? So the overall feature is a little bit different from cationic polymerization, right? Although it also have 3 distinct features, steps. initiation, propagation, but there is no termination in anionic polymerization. And in initiation part, there are three different ways to start this anionic polymerization reaction. Okay, so but the detailed mechanism study has not been done, and the major characteristic of this anionic polymerization is that it can generate almost monodisperse polymers, and you can easily calculate the average degree of polymerization. Okay, if you have information about the initial monomer concentration and also initiator concentration.